So what is linear probabilistic modeling? The term itself sounds terrifying. However, once we break it down, the concept becomes easier to understand. But first, we must understand the basics. The simple linear regression model uses the linear equation y equals beta sub 0 plus beta sub 1 x plus epsilon, where y is the dependent variable, x is the independent variable, and epsilon is the random error term that allows the point to be above or below the true regression line. The graph of this equation includes a line of best fit, which is made from the equation without the random error term, where beta sub 1 is the slope of the line and beta sub 0 is the y-intercept. Here is a random data example showing a simple linear regression model. Notice that on this graph, each point that is plotted has a certain amount of error that can be found by looking at how far above or below the point is from the line of best fit. Normal distribution also plays a role in linear regression because of the variance value of the set of data. If the value of the variance is high, then the points are expected to be spread out from the regression line. But if the variance is low, then we can expect the points to be close to the regression line. So that's great and all, but what does it have to do with linear probabilistic modeling? Well, for probabilistic modeling, we use the same equation. However, in this case, the dependent variable y can only be binary, meaning that it can only have a value of 1 or 0. In engineering, the values of 1 and 0 can mean many different things in areas such as quality control for a manufacturing factory. These results can be just about any binary outcome such as success and failure, accept and deny, and values could simply stand for yes and no. Okay, you may still be a little confused at this point, so let's look at an example. Imagine you're an engineer at Dunder Mifflin Paper Company, and Michael Scott asks you to find out if temperature has an effect on the failure rate of producing paper. If we get a set of data where the x value is the temperature and the y value is either 1 or 0, the first few samples will look something like this. After plotting our data, we can see that the probability of failure decreases as the temperature increases. From the equation of the regression line, we can use the slope to find the change in probability of failure with the addition of 1 degree of temperature. If we multiply 0.0116 by 100 to make it a percent, then we can conclude that each additional degree of temperature increases the chance of success by 0.116%. So, to wrap things up, linear probabilistic modeling is a special type of simple linear regression that is used to estimate the probability of specific binary outcomes that only have a value of 1 or 0. Thank you for watching.